Okay, so our speaker today is Ayten Koç, and her title, as you can see there, is a generic quotient of a Leavitt path algebra is isomorphic to a Leavitt path algebra. Please, Ayten, go ahead.
Thank you very much for the invitation. This is a joint work with Murad Özaydın, and who is here and also. Sorry. Our aim is to answer the question, when is a quotient of Leavitt path algebra is isomorphic a Leavitt path algebra? Also, we define a stratification and parametrization of the ideal space of a Leavitt path algebra, and also observe that a generic quotient of a Leavitt path algebra is a Leavitt path algebra. Along the way, we show that the lattice of the graded ideals of a Leavitt path algebra is a Morita invariant, hence independent of the grading. Contrary to most algebraic properties of Leavitt path algebras, our criterion for a quotient to be isomorphic to a Leavitt path algebra is not independent of the field of coefficients. Now let's fix some notation. Gamma here is a directed graph and also is called digraph. V is the set of vertices, E is the set of arrows, S and T source and target functions from arrows to vertices. And if V is not the source of any arrow, then we say that V is a sink. If our vertex V is not the target of arrow, then V is called a source. If target of an arrow E is also source of arrow, the same, then A is called loop. A digraph is called finite if the vertices set and arrow set are finite. To simplify the discussion, we will consider only finite digraph today. And a path P is a sequence E1, E2, En, such that target of any arrow is should be source of the next arrow. SP is the source of the path P is source of the initial arrow, and TP is the target of P is target of the final arrow. And also every vertex V is a path of length 0, of course, and the source and target is V. A path P is called cycle if source and target is C is a closed path, and also there is no and repeated vertex. An arrow E is called an exit of a cycle C if E is different from all arrows of cycle C, and also source of E as is on cycle C. Path algebra F gamma of a digraph gamma with coefficients in a field F is the algebra of formal linear combination of paths in gamma, where multiplication of two paths P and Q is defined to be their concatenation PQ if target of P is source of Q and 0 otherwise. Thus, a basis for path algebra is given by all paths in digraph gamma. Let's give the double digraph. Double digraph is obtained from the gamma by adding the dual arrow. Extended digraph has the same vertex set, and adding we obtained this extended digraph by adding the dual arrow, and E, for example, for all arrow in digraph, the corresponding dual arrows is obtained interchanging source and target, and we obtain the corresponding dual arrow. A Leavitt path algebra L gamma of a digraph gamma with coefficients in the field F is the quotient of the path algebra by the ideal generated by Kunz-Krieger relations. Kunz-Krieger relations 1, E star E is the target of E, E star F is 0 for all arrow E and F. CK2 for every non-sinc vertex V. V is the sum, E star. Sum is over arrows such that source of arrows should be V. And we can extend the star operator to all paths. V star is V for all vertex V, and Q is a path E1, E2, En. The dual path is noted by Q star, the product of dual arrows in reverse order. This defines a star algebra. This defines a star algebra structure on the Leavitt path algebra. And also Leavitt path algebra is also Z-graded algebra, and where grade of vertex 0, grade of arrows 1, grade of dual arrows -1. CK1 relation, Kunz-Krieger relation, implies that paths of the form PQ star span Leavitt path algebra, where P and Q are paths in gamma, with target of P is a target of Q. And also today we will consider only finite digraph. So Leavitt path algebra for finite digraphs has identity element, and identity element is sum of the vertices. Now let's give some example. Many well-known algebras can be described as a Leavitt path algebra. Let's consider the digraph, this digraph. Leavitt path algebra of this digraph is isomorphic to matrix algebra. Next one, let's consider only one loop. And Leavitt path algebra of this digraph is isomorphic to Laurent polynomial algebra. And the next one, Toeplitz digraph. Also, this is known as algebraic Hong-Szymanski two-dimensional quantum disk. And what's the Leavitt path algebra? Leavitt path algebra is isomorphic to Jacobson algebra. And another example, one vertex and loop. And Leavitt path algebra of this digraph is the original Leavitt algebra of type 1n. Now, I want to mention about the graded ideals. Let's give some definition about a subset of vertices. A subset H of vertices is called the hereditary if for all arrows for all arrows source of arrow is in H, then a target of arrow is also in H. A subset H is called saturated if the target of all arrows starting at V in H, then V is also in H. For any ideal of Leavitt path algebra, then we have intersection of J intersection V is hereditary saturated set. Now let's define the new digraph. Gamma over J is digraph obtained from the digraph gamma by deleting the vertices in the ideal. We have a star algebra epimorphism from Leavitt path algebra of gamma slash J to the quotient L gamma over J, defined by sending all vertices to the coset of vertices and all arrows to the coset of all arrows. So we obtain the star algebra epimorphism. This epimorphism is an isomorphism if and only if our ideal is graded ideal. And so we have a one-to-one correspondence between graded ideals of Leavitt path algebra and hereditary saturated subset of V given by sending an ideal I to the I intersection V and sending by any hereditary saturated subset to the ideal generated by this subset H. Let's skip. Now let's mention the two-sided ideals of Leavitt path algebras. This theorem says that for any arbitrary ideal J of Leavitt path algebra is generated by vertices in the ideal and by canonical generators where C is a cycle with no exit in gamma slash J, and f of C intersection J is a non-zero ideal of f of C. And here, the polynomial is the minimal polynomial of C in the corner algebra of quotient at the source of cycle C. This is a version of the Çolak-Ranga-Şivami theorem for row finite digraphs, but the original version was given by Çolak and then extended by Abrams, Bell, Çolak, and Ranga-Şivami, and then the final version given by Ranga-Şivami for arbitrary digraph. For arbitrary digraph, there is a third set of the generators which are breaking vertices coming from infinite emitters, but now today we have no infinite emitter in our digraphs. Our digraph. We have a stratification of the set of ideas of Leavitt path algebra indexed by the lattice of graded ideas, where the stratum indexed by graded ideal I is this set of ideal J, such that I is the greatest ideal containing J. We need to use a finer stratification indexed by the pairs I beta, where beta is the subset of the set of cycles with no exit in gamma slash I, contributing polynomials generators to J. And each stratum J I beta indexed by I beta is parametrized with a cardinality of beta tuple of finite non-zero F sequences, or equivalently with non-constant polynomials with constant term 1. We have a bijection between the ideas of Leavitt path algebra and triples I beta theta, and where I is a graded ideal, beta is a subset of the set of cycles with all exits in ideal I, and theta is a function from beta to polynomials, non-constant polynomials with constant term 1. The ideal space of Leavitt path algebra is the set of ideals of Leavitt path algebra equipped with stratification and parametrization given above. Now we obtain a new digraph obtained from the gamma slash J, and then we obtain this result if this new digraph is not, for example, lambda is the new digraph obtained from gamma slash J. How to obtain the cycles contributing canonical polynomial generators are loops without changing the isomorphism type of Leavitt path algebra of gamma slash J. That is, we have two and the digraph gamma slash J and lambda, different non-isomorphic digraph maybe, but Leavitt path algebras, their Leavitt path algebras are isomorphic. And now we define another digraph, gamma double slash J, related to the pair gamma, digraph gamma, and ideal J. This digraph is obtained from gamma slash J by replacing each cycle C corresponding to canonical generator of ideal J with a loop, as in the previous lemma, to get the digraph lambda. and then deleting the loop and replacing source of loop with degree of sinks, and each arrow ending at this source with degree degree f arrows, each ending at a distinct sink, replacing the loop. Now let's give one example how to construct the gamma double slash j. And our ideal is generated by this polynomial of C. And here alpha, beta, gamma distinct non-zero elements in F. Here J intersection with W. And let's consider this diagram. And gamma slash J, how to obtain? Delete all vertices in the ideal. And here only W, we only one vertex. And so we obtain this cycle. So as in our previous lemma, to get lambda, to cut this cycle at the initial arrow, at the target of the initial arrow, and then replace with this arrow a loop preserving the source at the same vertex. Sorry, and we obtain this lambda and gamma double slash j. And let's look at the degree of polynomial. Degree of polynomial is 3. So add two new things, 3 new things, and replace with v with v1, v2, v3, and delete this loop and replace each arrow ending at this source by the new arrows, 3 and degrees 3 arrows, each ending at the different things, new things, and then we obtain gamma double slash j.
Sorry,
Yes.
one question.
Okay.
So in J, in the definition of J,
Sure. Yes.
there is no W.
Yes.
But then you say that J intersection B is W. Who is
Yes.
W above? Is W SC or
not W here? C is
that cycle?
C is this cycle, and the W the target of this arrow. And we know that this is a polynomial generated by this polynomial. We know that it is a fact if and the C is the gives a generator polynomial, and then if there exists one path from the C to any vertex, these vertices should be in the ideal.
Okay.
So and also
I see.
all vertices and these type vertices, not on the cycle C, but there's a path from the source of this cycle, from this cycle to any vertex under this cycle. So all of them, all vertices in the R ideal.
Okay, thanks.
So we obtain gamma double slash j, and then now let's give the definition of DLF ideal. An ideal J is DLF if each canonical polynomial generators is product of distinct linear factors. And so an ideal is graded if and only if it has no canonical polynomial generator. Hence, it is vacuously DLF. Then we obtain the main theorem. For any ideal J of Leavitt path algebra, the quotient L gamma over J is isomorphic to Leavitt path algebra if and only if the ideal J is DLF. In this case, the quotient L gamma over J is isomorphic to Leavitt path algebra of gamma double slash J. And the sufficiency of our criterion implies that a generic quotient of a Leavitt path algebra is isomorphic to a Leavitt path algebra. And Ji beta is a product where each factor corresponding to C in beta is parameterized by the non-constant polynomial with constant term 1. We filter these polynomials by degree and identify the n level of the filtration with non-zero finite sequence. The topology on fn set minus 0 is the Zariski topology or the Euclidean topology if and the field is the complex numbers. The topology on each factor is generated by topologies of the subspaces fn set minus 0, that is, a set is open if and only if its intersection with each subspace is open, and the topology on Ji beta is the product topology. And we obtain this result if our field is algebraically closed, then the set of DLF ideals in each stratum, Ji beta, is open and dense, hence generic. Now let's give some examples. Let's consider only one loop. And we know that the Leavitt path algebra of this digraph is Laurent polynomial algebra. If characteristic of field F is not 2, then L gamma, the quotient L gamma ideal generated by V minus E square is the isomorphic to Leavitt path algebra of gamma double slash J, and where gamma double slash J is this one, and our polynomial 1 minus x square, degree is 2. So, and replace this loop by 2 isolated vertex, and then we obtain our result. Okay, this and the digraph. However, the quotient, the Leavitt path algebra of gamma over the ideal generated by the square V minus E is not isomorphic to Leavitt path algebra for any field F. So depends on the field of coefficients.
So another question. So here, one algebra is separable and the other one isn't, right? Because the polynomial that defines it is separable. Is this always? I mean, does this give a taste of what happens in general?
Sorry, again, please.
Yeah, there is a definition of when an algebra over a field is separable.
Separable.
Separable, yeah. For a commutative algebra generated by one polynomial, this means that the polynomial has no multiple irreducible factors.
Yes.
Which is similar, I mean, to what, I mean, it seems to be related to what you have here. But, I mean, here, and since the algebra is commutative, is precise and is generated by one polynomial, then this is precisely that. But I mean, for a general Leavitt path algebra, you are asking some separability condition on some commutative subalgebras generated by the cycles. Not on the whole thing, because the only Leavitt path algebra that is separable is a sum of matrices. So in general, separability for an algebra that is non-commutative means that it is projective as a bimodule over itself. That's the general definition. Just, I was wondering if you had considered this, but if you haven't, never mind.
No. Okay. And next example, and digraph the same isolated and loop, and take the real numbers as our field. Then the quotient L gamma over this ideal is generated by V plus E square. E square is not isomorphic to a Leavitt path algebra because the roots of the canonical polynomials, polynomial 1 plus x square are not real. But if we take the complex numbers and then L gamma over these the same ideal, these same quotient, but coefficient fields complex numbers, and this quotient is isomorphic to Leavitt path algebra, a Leavitt path algebra, and also this one is isomorphic to C2, and the where and the lambda here gamma slash J is just only isolated two vertex. This graph. And now let's consider another example. Let J be this ideal generated by the vertex we choose. So there is no canonical polynomial W2, sorry. J has no canonical polynomial generators since J is a graded ideal. So what's the quotient? L gamma over J is isomorphic to L gamma slash J is isomorphic to how to get this digraph gamma slash J, delete all vertices in J, so delete this and the W2, vertex W2, so we obtain D2. So, and is isomorphic to Leavitt path algebra of quantum disk, two-dimensional. Let's skip.
Hepsini yap, hepsini yap. Çok zamanında.
Okay. And another example, five-dimensional Hong-Szymanski five-dimensional quantum sphere. And if take the H is this set and our polynomial 1 minus x square, and J is generated by H and this polynomial of the C2 cycle or here loop. And so we obtain gamma slash J, deleting the all vertices. So we obtain S3. And if characteristic of F is not 2, so and the quotient L gamma over J is isomorphic to gamma double slash J, and gamma double slash J is quantum sphere, and then this digraph. So we obtain the quotient is isomorphic to a Leavitt path algebra, and also Leavitt path algebra of this digraph. If characteristic is true, the same for the same example, L gamma over J is not isomorphic to Leavitt path algebra because the roots of F, this one, are not distinct.
So, sorry, if you further divide, so when you divide by this polynomial that has multiple roots, you get some nilpotent element in the quotient. So if you further kill that one, you divide by that nilpotent element. Do you get a Leavitt path algebra?
Repeated root and this ideal
Yeah.
is...
Suppose you not only divide by, so in this case, I think it was x squared minus 1, right? So
x squared minus 1?
Yeah, 1 minus x squared. Okay, so this is in characteristic 2, this is 1 minus x squared. The square 1 minus. Okay.
Yes.
Now you can, so in the quotient you get that 1 minus x is nilpotent of index 2. Now
Yes.
suppose you further divide by 1 minus x. So you get x equal to 1.
Yes.
So that means, what does that mean? That you make V2 equal to C2.
Yes.
So in that case, do you get a Leavitt path algebra when you further do that?
Yes.
Okay. So the difference is that you get some nilpotent extension of a Leavitt path algebra.
Yes. Yes. Yeah.
Okay. Okay. Thanks.
Another example, consider the same digraph, this one, 5-dimensional quantum sphere, and take the H is the set of only one vertex contains only one vertex V3 and the last vertex, and take this polynomial 1 minus x, and J is this one. Generated by H and this polynomial of C2, let, and so gamma slash J is this digraph, and L gamma over J is isomorphic to gamma double slash J, and also yes, the answer of your question here. And quotient is isomorphic to Leavitt path algebra of gamma double slash J, and this digraph is the Toeplitz digraph, D2. And another example, let F be a field containing the n roots of unity, characteristic F not dividing n, and our polynomial is 1 minus xn here, and consider this diagram. If our ideal is generated by W and this polynomial, and then gamma gamma slash J is a quantum 3-dimensional quantum sphere we obtain, and deleted this vertex and arrow, and we obtain this one. So gamma double slash our ideal J is we obtain this one. Yes.
So sorry, in the D4Q graph there.
This one.
Yeah. No, above.
Oh, sorry.
No, above. Go up. Above. Up. No.
This one.
D4Q. That one.
Yes.
So shouldn't there be a cycle without an exit there? What's the cycle without an exit?
There is no cycle without an exit. Every cycle here an exit.
As an exit, yeah.
Yes.
And then
our aim is to get the gamma slash J to get the cycle with no exit and here. So this one is the canonical polynomial generator. Every canonical polynomial generator and corresponding any cycle given a canonical polynomial generator without exit in gamma slash J.
Okay.
This one is gives the canonical polynomial generator for J, ideal J. There is no exit.
Okay, but okay, so you start with okay. No, I thought I'm confused because at the beginning the parametrization or the real space was identified. I mean, in case there was cycles with an exit, without an exit, then these polynomials at cycles came in. But since there are known,
sorry, wait, please.
In the Rangaswamy.
Yes, Cholak and
theorem.
Rangaswamy theorem. Every two-sided ideal generated by vertices and canonical polynomial generators, and here C is a cycle
Without
with
exit.
yes, in gamma slash J, and means with all exit in J.
Not in gamma, not in gamma, in gamma slash J.
Yeah,
Okay.
yes.
Yeah. Sorry.
İn aşağı.
This one, the last example. So, and gamma this one, gamma double slash J, and this cycle has no exit in gamma double slash J. And this one is gives the canonical polynomial generator for and our ideal J. And a Leavitt path algebra. Leavitt path algebra of the quotient is isomorphic to Leavitt path algebra of gamma double slash J. And now let's explain our lemma. It is important, I think, and to construct the lambda and gamma double slash J is this lemma. We define the new digraph lambda obtained from gamma slash J. Have to obtain lambda and take the collection of distinct cycles with no exit in gamma slash J. Then we obtain the new digraph lambda, have to obtain, and cut this is a collection of distinct cycle. For example, take the C, one cycle C, cut this cycle at the target of the initial arrow, and replace with this initial arrow to a loop such that and the loop source of the loop should be source of the initial arrow. And then we obtain lambda and L gamma slash J and L lambda is isomorphic. For example, to illustrate this lemma, have to obtain the lambda. Let's consider this digraph. This digraph has only one cycle. EFG or FGE is the same cycle. And we obtain three possible digraph lambda. Take this cycle, for example, EFG, first initial arrow E, cut this cycle at the target of initial arrow and in this at this vertex. So replace with this vertex and this arrow at a loop at the same source. So we obtain this loop, EE prime. So we obtain the first and this digraph lambda, and we claim that Leavitt path algebra of this digraph and also is isomorphic to L gamma. And take the another, for example, take this cycle, but if FGE initial arrow F, and they cut this cycle, the initial, the target of the initial arrow. So we obtain a new and a loop at this vertex. So we obtain the second digraph. If we take the GEF, and initial arrow of this one, cut and this cycle. So replace G with a G prime, and we obtain the last digraph. We have four digraphs are not isomorphic, but their Leavitt path algebra are the same, are isomorphic to 5x5 matrix algebras with entries coming from the Laurent polynomial algebra. And let's stop here. Thank you very much for your attention.
Thank you. I missed the part. So you mentioned that the lattice of graded ideals was
Morita invariant.
Morita invariant. Where did you
Yes.
where did you mention this during the
Yes.
talk?
I skipped this slide. Sorry. This slide. Yes. In fact, the lattice of graded ideals of Leavitt path algebra is Morita invariant, since we have a lattice isomorphism between the lattice of graded ideals and the lattice of the closed submonads of non-stable K theory, given by sending I perp. I perp here. I perp is the isomorphism classes of finitely generated projective modules, such that all homomorphism, there is no non-zero homomorphism from P to R over I. And also we know that in the non-stable K theory is an additive monoid of isomorphism class of finitely generated projective R modules under direct sum. This VR is a Morita invariant, and also use and this isomorphism. So the lattice of graded ideas of Leavitt path algebra also Morita invariant.
Wasn't this isomorphism of lattices between V of the Leavitt path algebra and of lattices of what submonoids or
closed submonoid,
closed submonoids, and the graded ideals not previously known? I mean, I know that
no,
there is some. I have seen this that there is some connection between. Yeah.
Hi. In my joint paper with Perriar and Maria Angeles Moreno, we showed that the lattice of graded ideals of the Leavitt path algebra is isomorphic to the lattice of ordered ideals of the monoid. So essentially, it's that what are you looking for? It's a different lattice, but essentially the same thing. And certainly, the two Morita equivalent algebras will give you up to isomorphism the same monoid. So essentially, this is the reason that graded ideals are Morita invariant.
Yes.
Yeah. So V of R is Morita invariant as an ordered monoid or preordered.
Yes.
With the algebraic order, yes, that's right.
Yeah, so this is a different outlook of the same property, because you use a different lattice.
Yes.
Okay, so are there any further questions or comments by the audience? Otherwise, we'll stop the recording here.